another one is for research. So there are two types of node. One is process. We are going to use the circle to represent the process. We are going to use the rectangle to represent the research. Two types of node. So which means we consist of the P and I. And edges is the two types of edge. Request edge means it's not assigned yet. Process 1 requests the resource J. And if that is assigned, it's from the resource to process. This resource is assigned to the process. So let's take a look at the example of this one. Oh, by the way, what if we have the multiple instances? Like for example, this is a hard disk drive. I have 4 hard disk drives. Hard disk drive 0, 1, 2, 3, 4. At the time, you can use the small rectangle inside the resource. And this is a process. This one means process I request. We don't know which instances will be allocated. So because we have 4 of them, so to the outer rectangle. Pi request ij. Then this one means this first instance is allocated to the Pi. In other words, Pi is holding this instance. So we are going to use this graph, resource allocation graph. Let's take a look at this resource allocation graph, which means P1 is holding R2, right? At the same time, requesting R1. Unfortunately, no available R1. It has only one instance. It's held by P2. Also, P2 is holding R2. Okay, then P2 is requesting R3, and R3 is held by P3. Can you understand the graph itself from the notation of this one? This is a resource allocation graph. Let's check whether this is a deadlock or not. Okay? We don't have to worry about too much. Okay? Mutual exclusion. Mutual exclusion is satisfied with the mutual exclusion in our definition. And hold and wait is a hold and wait. And third one, no preemption. We don't want to cancel the allocated graph. So we can check the last one. Okay, whether circular weight or not. Circular weight, finding circular weight actually is not easy. So that is the reason we'd like to use the graph data structure. So is this circular weight? Let's see. P1 is holding R2 and requesting R1 is held by the P2, and P2 is holding this one. So it looks like the circle. However, there is the open, the graph, subgraph. So which means P3 eventually terminated. Then we release R3. Once R3 is released, P2 is acquire this one. Then eventually this will be completed. Then P2 is done. Then this one and this one is released. Eventually P1 is completed. So this time, this is not circular way. There is no problem in terms of deadlock. This is not the deadlock situation. So we can easily understand current process state using resource allocation graph, the graph structure. What about this? So first, the 3 requirements you don't have to worry about. It's already satisfied. So we need to check the circular weight 1. So it's the same thing, but P3 is requesting R2. So it is circled. Okay, which means this is the deadlock event. So it satisfies the all 4 requirements. So key part is whether we can find such a circular weight or not. In other words, in case find, we can do something That is the deadlock situation. And 3. Before we move to the next graph, looks like the very powerful, so it's easy to understand. There might be a problem. What can be the problem? Is there anyone who has more than 100 Facebook friend? No? Nobody use the Facebook? Let's say that you have more than 100. So if you draw such a graph using yes, there might be 2 actually. So can you find the circular way? Not easy. You can do the programming. How can you implement? For each node, you need to check all the other nodes, whether circular one. The next node, check. And next node, check. Complexity, if you have n number of nodes, it is n squared, n to the power of 2, which means it's the worst case, kind of brute force. Takes a long time, not long time, it's a very complex. In terms of the complexity, big O notation, it is n squared. So it's very high. So it's a very complex. So graph theory is graph something. Graph algorithm is usually NP-hard problem. What is NP-hard? You never heard about? That's the problem. And anyone? What is an NP-hard problem? And what NP stands for? You know, probably. I found you. What is an NP-hard? Your friend said. Then you can answer. Why don't I ask to him? NP means non-polynomial. It's a non-polynomial. Means what? Polynomial means it can be optimized. Okay? Using linear algebra optimization process, you can optimize. NP non-polynomial means there is no optimization. There is no way. Instead, brute force way, like the n squared. So that problem is usually very, very hard. Okay? Hard means more complex. Okay? So brute force way is one of them. So it takes a long time, relatively. So that is NP-hard problem. Like the binary search. Binary search is log n, right? It's not brute force. You can reduce the complexity. It's optimized. But graph theory is an NP-hard. If you implement that, it takes a long time. That is a problem. We will see what caused the issue, such an NP-hard problem. So graph theory, graph structure is good for representing complex data, but problem is it's an NP-hard problem. Most of the graph theory, like the subgraph clustering, graph cut, subgraph matching, searching such a circle is NP-hard problem. Not always. There might be some the optimized, the graph theory, the matching algorithm. Okay. By that time, you need to consider some constraint, condition, or assumption. Okay. So we can say we can change it. Restate the definition of the deadlock, especially for the circular way. So whether we can find the circle from the graph, such a resource allocation graph, whether we can find the circle or not. If we can find the circle, and if we cannot find the circle, that means no deadlock, right? So if you cannot find any circle, that means no deadlock. There might be no problem. You can process the request or allocation, whatever. However, if you can find the circle, that doesn't mean always deadlock situation, deadlock event. Like this one. Even though we find the circle over here, because of multiple instances, it can be solved. There might be no problem. So, in case of the circle, even though we find the circle, that doesn't mean always the deadlock. It can be deadlock or not. So, our goal is first need to find such a circle. Then, in case to find the circle, we may consider that may cause the deadlock situation. Okay, so if we can find the circle, so from the such a resource allocation graph, it may cause the deadlock or not, depending on how many instances are available. Otherwise, if there is no circle in the graph, so that may not cause any deadlock situation. So, how to handle such a deadlock event, we already see. So one of the solutions, that is the deadlock prevention. How? We can break one of the requirements. Okay, hold and wait, the mutual exclusion, and don't preemption, and what the circular weight. We can break one of these, then there might be no problem. That is preventing the deadlock. Another one is the deadlock avoidance. We will see details, but the deadlock avoidance means before you enter the next state, which means I'd like to, so I'm the operating system, you are the process, so you are requesting the resource. Okay? Before I allow for that request, okay, check whether your request may cause the deadlock or not, based on the current state, process and resource state. How? How can you check? Graph, resource allocation graph. Check the resource allocation graph, whether there might be circle or not. If circle, no, you cannot request such a resource. Okay? Avoid such a request. Otherwise, there might be no problem. I cannot find. In case I allow the process take the resource, there's no circle, then allow to request and get the resource and proceed to the next one. These two never enter the deadlock event, never cause the deadlock situation. Looks like the good, but not always a good solution, always. The other is, if he requests the resource, allow, you can take the resource. Okay? You can take the resource, whatever, then do not take a look at my first. It belongs to me. Then check. Okay? You can request. Then from time to time, check whether there exists a deadlock or not. You'd like to detect. So what is the main difference between this approach and this approach? This one never enter deadlock, but this one may enter deadlock. Which one will be the good solution? Upper, first, or second? No operating system use these two. Even this, no. Then why do we need to study? No operating system. What is the main problem of this? NP hard. This one does not make sense. Okay? This one, avoidance and detection. Anyway, you need to find whether there exists a circular weight or not. It's a very, very expensive job. Okay?
But while detecting, we are still checking if there is a deadlock.
No.
What are we detecting?
We do not detect. That is the current operating system. The modern operating system, because it's too expensive, detect or the avoidance. To avoid, you need to check whether this request causes the deadlock or not. Check. It takes some time. It's very expensive. So current operating system actually ignore deadlock. You may request each other, you love each other, and cause the fighting or the kill each other, doesn't matter. Okay? Who is in charge of that? It's you. So you can fight your friend for girlfriend, it doesn't matter. Okay? Or if the operating system involves such a deadlock event, your operating system will be slower and slower. So actually operating system currently ignore the deadlock. Instead, each application, each user is in charge of that. How? Java has the exceptional code, so you can check the exceptional code, or from time to time you Control C, interrupt, send the interrupt signal and stop the current process. Okay, that is the reason so many Control C, and sometimes you turn off your system. So that is, but sometimes you need to do such a detection and avoidance depending on the operating system. Okay, so we will see such a avoidance and detection algorithm.
No, what I was asking that
Yes.
for the detection,
Yes.
we are still checking if there is a deadlock or not, right?
So it's quite similar. We will see it's quite similar. However, avoidance, we do not allow to request. If check he wanna request another resource, okay? Resource of this one. Check whether this request cause the deadlock or not. If you decide it may cause the deadlock, which means you find a circle, then no, you cannot request this one. That is the avoidance.
What is the detection?
Detection, you allow, you can request. So he is asking this resource. Then sometimes periodically, your operating system, I'm checking whether there exists a deadlock in this current status. Okay?
But if it exists, then what does it do?
Then do something that is called the recovery. We will see how to recover. Okay? Don't be confused. The avoidance and detection quite similar, but avoidance never entered the deadlock. Before allow, you need to check the deadlock situation, circular wait. But detection, from time to time, detect all the process and the resource state, whether there exists a deadlock or not, current state. Okay, so we already talked about the deadlock prevention. And deadlock avoidance. What time is it? It's end 4:30? Oh, 5 more minutes. I think I can explain the deadlock avoidance. Okay. So deadlock avoidance one more time. So we try to avoid, we not enter. So every time a process requests a resource, check whether this request caused the deadlock one. Okay? Before grant. If it's okay, there is no the circular way by considering his request, no circular way, then allow grant to get it. That is the deadlock avoidance. Then how can we check? So to do that, we need to we need to consider a number of available resources and how much of them are allocated and how many resources are needed. So let's take a look at the one. So for example, currently P is 0, process 0, process 1, process 2. Currently we have this, and process 0 needs the 10 magnetic tape. Nowadays nobody uses the magnetic tape, but still use for what? Backup. Buffer. Don't believe the hard disk drive, traditional hard disk drive, is like the disk and disk comp, okay? Because once the head touch the surface, there might be the bad sector, and you may lose the entire data. Okay. Also, the SSD is not forever. So sometimes later, once actually memory based, memory need the power. So you may lose sometimes later, maybe 100 years later, you may lose the data that is the SSD. So magnetic tape, one of the cheap and affordable and reliable method to keep the to back up the data. Anyway, so suppose the P0 need to be completed 10, P1 need 4, P2 need 9. Okay, but only 12 are available. Currently, P0 is taking 5, P1 is taking 2, P2 is taking 2. So how many available resource? 9, 12 minus. So currently 3 are available. This is a current state. So if you can find the list of process, whatever, P1, P2, P3, okay, without deadlock, okay, that means this is called safe state. Okay, the safe state means without deadlock. Okay, our goal is to find whether safe state or not. Deadlock avoidance, if he requests the resource that the request cause the safe state or not. If safe state, yes, okay, allow, right. Otherwise, no, decline the request, avoid such a request. So how can we find? So if we can find the list of, at least one list of process that can be terminated. So let's take a look at the current state. Is this safe state or not? First, 3 are available. We can execute the P1 first. So P1 can be terminated, and 4. So 1 is available, 4 need. Then once terminated, 4 will be returned. So it will be 5 available. So this is done. Then P1. The next P0. P0, 5 needed, so will be terminated. Nothing 0, 10 is done. It will be 10 will be returned. So 10. Then P2. So we can process P1, P0, P2 in order, which means it's a safe state. There is no deadlock situation. What if? It's exactly the same thing, but P2 requests 1 more. So if I allow the P2, it will be 3. And how many available? 1 available. Can you find any process that can be terminated? No. Which means it's a circular way. So it's a deadlock. So before I grant his request, P2 request, check whether safe state or not. So this is not safe state. So decline his request to avoid deadlock. So this is the deadlock avoidance using resource allocation graph. Okay. So next class we will see details of the avoidance. That is one example. So we will see the banker's algorithm to detect such a deadlock for the avoidance and the detection and recovery algorithm. Okay. We will see you on Thursday.